Okay, welcome to the video for chapter 8.1 vectors in kinematics. So previously we looked at kinematics in year 1 where it was mainly in 1 dimension. We're now going to apply that to 2 dimensions using vectors. Okay, we've looked at some of these ideas already in chapter 6, but let's build on them here. So first of all, we've got this equation. So when the velocity is constant, we can use this equation here. R, which is the position at time t, R naught is the original position, the start position. V is the velocity. Remember, it's constant velocity in this case, and T is the time, as you would expect. Okay, so let's put this onto a little graph. So this is going to be your J component here. This is going to be your I component. You can sometimes think of this in terms of east and north, depending on the context of the question. Right, so we've got this start position. So let's say I'm starting here. We'll call this R naught. Then it's moving off at a vector V. So let's say this was my V. So that will be 1V. And then that will be after 1 second. Then it will go off in V again. That will be after 2 seconds. V again, 3 seconds, etc., etc. And you can see it's created this straight line graph. Okay, and this straight line graph is kind of like this one, so it's almost like a y equals mx plus c equation. Right, let's apply that to an example. Example number 1. Okay, example number 1. We have a particle starts from the point position vector 3i 7j. So let's put this on a little graph so we can visualize it. As I always say in mechanics, diagrams are very useful to help you understand the nature of the problem. Okay, so you've got this original vector, so 3, so this is j, this is I, and we can think of this again as east, and this is north. 3, 7 is going to be somewhere up here, so this is R naught, and it's going to be travelling at velocity 2I minus j, so it's going 2 across for 1 down. So that'll be after 1 second, 2 seconds, this is going for 4 seconds, 3 seconds, 4 seconds. Okay, and we want this position here, which we're going to call R. Okay, so we can use this equation. So R is equal to start vector 3, 7. I'm doing it as column vectors rather than I and J vectors. Just think it's easier to do it that way. Plus the velocity 2 minus 1 times time 4. So 3 add 2 times 4, that's 3 add 8 is 11. And 7 add 4 times negative 1, 7 minus 4 is 3. So the position after 4 seconds will be 11.3 meters. Okay, we're now going to carry this on. So we'll find the time at which the particle is due east of the origin. So it's when it crosses this axis here, so the y-axis or the x-axis as it would normally be. Okay, so we want to know the position here. So we don't know, the coordinate will be along the I, we don't know, some value x, but the j we know will be 0. Okay, so let's put that into my r here. x0 is equal to r naught, 3, 7, plus 2 minus 1, plus some time t, which we don't know. Okay, now we don't know this x, we can't work it out, but we can just break it down into this j component. So we can say 0 is equal to 7 minus 1t. So therefore t must be equal to 7. And that would be your answer. Okay, so that's example 1. Right, moving on to example 2. Example 2. Right, so example 2 has a constant acceleration. So this is like your Suvat style equations. Notice we can use these equations here. V equals u plus at, which is one of the Suvat equations, and this is r equals ut plus half at squared. Now r is just the same as displacement, but it's in 2 dimensions, it's in vector form. Okay, so there's nothing different here to Suvat. We're just using those same equations. And we can use those equations because acceleration is constant. Particle P has a velocity of -3I plus j at time t equals 0. It's got an acceleration 2I plus 3j. Find the speed of the particle on the bearing on which it is travelling at the time t equals 3 seconds. So if I just write my Suvats over here, I don't know s, but I do know u. So that is -3 1. V is what I'm trying to find out, the speed. A is 2, 3, t equals 3. So I can use this first equation here. So V is equal to -3, 1 plus 2, 3 multiplied by 3. So -3 plus 6 is 3. 1 plus 9 is 10. Okay, so the velocity at time equals t is 310. Now it wants the speed. We want the speed, which is the magnitude. So let's put that into a little thing. So we've got 3 across and 10 up. We want to know the speed here. Speed equals the root of 10 squared plus 3 squared, root 109, which I believe is 10.4. And we want to know the bearing. The bearing, now remember bearing comes from the north, so here's the north arrow. We want to know that angle. Okay, so if I just change here, now we can work out this angle here is going to be the same as this angle here. So we'll call this theta, this theta here. So theta is equal tan to the -1, and opposite would be 3, and adjacent would be 10. So that gives you an angle of 17 degrees to 2 significant figures. So the bearing is equal to 0, 17 degrees. Okay, moving on to example 3. So here's example 3. Ice skater is skating on a large flat ice rink at time t equals 0. Skater is at a fixed point and is travelling with a velocity of 2.4I minus 0.6 meters per second. Time 20. This is a velocity relative to the skater's position vector s time t. Modelling the skater as a particle, find the constant, the acceleration of the ice. So initially we have, let's just write down what we've got. S equals s, u equals 2.4 negative 0.6, e, this is at 20 seconds, 0.4, that is what we're trying to find out, t is equal to 20, so we can use v equals u plus at. Got this the wrong way around, sorry about that. That's 5.6. So I can work out both of these components. Put my calculator here. So to work out the top component, I'm going to do negative 5.6 minus 2.4 divided by the 20. So that's negative 0.4. And then 3.4 minus negative 0.6, that's plus 0.6, divided by 20 equals a fifth of 0.2. So that's the acceleration, meters per second squared. So part B, expression of S in terms of T. Okay, so I can use my other equation, S equals ut plus half at squared. So S is equal to u 2.4 negative 0.6 t plus half times negative 0.4 0.2 t squared. So I can write that in one vector. So half of 0.4 is 0.2, so it's minus 0.2 t squared. And this is minus 0.6 t plus 0.1 t squared. Okay, so there's your expression as a vector. Moving on to part C. So the time at which the skater is directly northeast. Okay, so here's north. This is your J component. Here's east. This is your I component. Northeast is in between. And this is on the line y equals x. Use a different colour here. Okay, so that means that I component is equal to the J component. So for part C, I can simply write 2.4 t minus 0.2 t squared is equal to negative 0.6 t plus 0.1 t squared. We've got a nice quadratic here. And take that over there, 0.3 t squared. Take that over there, minus 3t. Times by 10 and factorise. So you've got 3 outside, t outside, t minus 10 there. So t is equal to 0, which would be the start. So I'm not going to use that one. Or t is equal to 10, which would be the time when he's due northeast. Okay, moving on to the final part. Let's move this up so you can see it. Part D, the second skater travels so that she has a position of 1.1 t minus 6. 1.1 t minus 6. Okay, so the position here is going to be r is equal to 0 on the I component, 1.1 t minus 6 on the J component, and that's going to be in the same position as this one here. So S is equal to 2.4 t 0.2 t squared. Okay, so let's start with the top one. So we're just going to break it down into its I component initially. 0 is equal to 2.4 t minus 0.2 t squared.